new to learn. If we say it's symmetrical, what do we actually mean? Okay. So where the shear force is applied, where I'm drawing the orange line now. Okay. Right. The force go through the what? Go through the centroid. Okay. It goes to the centroid, and the left-hand side geometry and the right side geometry, you can see down here are the same. Okay. So if I were to draw our transformation, if we were now to sketch our transformation, X, Y, and Z, right? The bending, okay, the deflection will only occur in the XY plane. Okay. So what do I mean by XY plane? If you look at the deflection will only be on this plane that I'm shading in green. Okay, so it's a vertical deflection. Every deflection is parallel to the plane over there. Okay, so this is the condition of symmetrical bending. So for this case, right? For this case, what we tend to do is we tend to calculate our shear stress is equal to Vy over Izz, right? Qz divided by T, okay? So far, when we use this equation, right? If you have not realized this, our deflection only occur, okay? Deflection occurs only. Okay, so there's a displacement. Okay, there's a vertical displacement about the y-axis. Okay, so deflection occurs only in the x, y plane. Okay, so that is what we call condition of symmetrical loading. Then we have another condition. I'm going to show you the condition of unsymmetrical loading. Okay, so I'm going to copy this. So what you see over here right? What you see over here is the condition of unsymmetrical loading. So if I zoom out, can you see the difference? Yes or no? Can you see the difference? What is the difference? Anyone? What you will see is both, right? The common thing is both have deflection, right? But the unsymmetrical, the deflection is not just on the what? YZ plane. Okay, the deflection is not on the YZ plane. So what you realize that the deflection is not just in the XY plane. Okay. Now, why is that? Why is that? So what you see over here, right? You will see that there is a twist, okay, about the x-axis, right? You can see there is not just a vertical deflection. There's also a what? A twist. Okay, you can see a twist. So why is there a twist in this case? Okay, so again, before I teach anything in detail, I like to explain to you why there's a twist. Okay, so again, this is the figure on the right is our cross-sectional view. So likewise, the force, okay, the force is still, the shear force is still applied on the centroid. Okay, is you still have a what? Centroid. Right? So what will happen is there's a twist, okay, there's a twist in this direction. The twist seems to be coming down this way. Okay. So if I call this side left-hand side, and I call the other side right-hand side, can anyone tell me why the twist is on that direction? Yeah, no, I thought she put away. Anyone? Yes. Yeah, you're partly right. Okay, more area is a very good. So in terms of rigidity, right? So if we relate this to second moment of area, okay, which side has a higher second moment of area? The left-hand side or the right-hand side? Which one have a higher second moment of area? Anyone? The left-hand side, yes? Right? So the left-hand side has more resistance to deformation than the what? Than the right-hand side. Okay, so the right-hand side have lower second moment of area. So IE is less what? Less rigid. Less rigid meaning that you need less force to induce what? Deformation. Over here, the left-hand side, higher second moment of area, right? So it's going to be what? More what? Rigid. Okay. So that is why the twist is in that direction. Okay. Now, the next thing is this, okay? Like typical engineers. Like typical engineers. How are we going to apply that the shear stress is equal to VQ over what? IT. How are we going to apply this formula? Okay. So far, we have been doing shear force since what? Week what? Did we do shear stress since week 4? Yeah, we started doing shear stress since not week 4. We started doing shear stress since week 3, Friday, right? So now we have been doing this, putting this formula, shear stress is VQ over IT. Okay. Now this formula is only valid when there is no twisting. Okay, so no twisting is allowed. Okay, engineers are like my daughter who is 5 years old. You tell her no, she'll say yes, she'll do it again. So like a typical engineering issue, we are going to force a square peg into a round hole. You guys will say, you're really not funny today. Right? So we are going to force, okay, I'll use this term. Okay, we are going to force a square peg into a round hole. What I'm trying to tell you is this. The good news for us is this, okay? We are not going to learn any more new formulas. We are just going to force this into the formula that we have, okay? It's a very interesting thing that is happening, okay? So I'm going to take another diagram. So how are we going to force to apply, okay? So now, this is how we're going to apply. Yeah, again, all these diagrams are available. Okay. And you have to see the diagram side by side, then you will understand better. Okay. So what we are going to do, okay, we are going to place, okay, we are going to place a fictitious block in the analysis. Okay. So we're going to shift, right? We're going to shift the load P, right, by a distance E, okay, from the centroid. Okay, so E is the shift distance, okay? Not necessarily the center weight, the shift distance to induced a counter moment. Okay, to induce a counter moment. Okay, so O, as you can see, the over here, right, is known as our shear center. Okay, it's known as our shear center. Right. So what we are trying to do is this. Okay? What we are trying to achieve is this. If we have a twist, the only way to untwist this is to apply Newton's third law. Right? Newton's third law is action equal to reaction. Right? Same in magnitude, but in different direction. So we are going to introduce a moment to induce, okay, to induce a counter twist such that the structure will only deform in the XY plane. Okay, so the counter over here, okay, the counter twist is to get rid of the twist due to the poor rigidity of the structure. Okay. Okay. Right. So from here, what we are going to do now, okay, so from here, okay, so we are going, so the basic concept is to induce a counter twist, okay. So what's happening down here, you see over here, if we have a shear force applied over here, okay, what we are doing is we have to design our shear force first. So all these are our shear force Q, or for this case, we call it V and F. Okay. So from all this shear force, we need to calculate the distance E. Okay. So what I'm going to do, I'm going to stop over here. We'll continue again on Friday. Okay. Thank you. Good luck for your exam or term test you're going to have later today.